Okay, so just to recap, for binomial theorem, there are two fundamental elements you need to be aware of. First is the action of factorial, something like this. So the notion of factorial is that it will do a calculation of a product from n all the way to 1 itself. So for example, if I say 5 factorial, it's actually saying 5 times 4 times 3 times 2 times 1, giving me 120. If I say 3 factorial, this will actually be 3, 2, 1, giving me 6. If I say, and the special case is actually 0 factorial. 0 factorial is known to be equals to 1. Okay, this is a definition of a new formula to evaluate something. You cannot dispute why is it like this. Okay, just accept it as it is. It's just a notation that people created to streamline certain evaluations. So n factorial. Okay, so I'm sure you have seen this in school already. So the next thing is actually something called n choose r, written like this, or you can write it as NCR. But the preferred notation when it comes to using binomial theorem, right, is actually this one, in my opinion. Okay, so this is pronounced as n choose r. Okay, so fundamentally, right, on a formula basis, this actually is actually evaluated as n factorial over r factorial n minus r factorial. So to give you a numerical example, 5 choose 3 is actually 5 factorial, 3 factorial, 2 factorial, because 2 factorial because it's 5 minus 3, okay? And if you can press this on the calculator, this will just give you 10. Okay, so I'm sure you have seen this before already. The n choose r, right? What does it actually do, right? It literally means what its name implies. So suppose if you have 5 football players and you need to choose 3 to come out and be your first team, right? The number of possible combinations you can achieve out of a pool of 5 players is 10. That's what it means. Okay. So again, if you have, let's say, if you have 11 football players, you need to choose 2 to be your strikers. The number of possible combinations is 11 factorial over 2 factorial, 9 factorial, giving me, give me a minute, 55. So there's 55 possible combinations of 2 strikers from a pool of 11 football players. Okay. You may dispute that how come I need to go through the formula, right? Because might not just evaluate everything on the calculator, because there may be certain questions that will ask you to evaluate n or r when they are unknowns, and you need to use the formula then, okay? For the sake of answering certain questions. So let's just be aware of them on a fundamental level will do for the time being, okay? There are some special properties of n choose r that you need to be aware of also. So this is the first one. N choose 0 is always equals to 1, okay? The number of ways to choose 0 players from a pool of n players is don't choose at all. So there's still one way, do not choose at all, to walk away, okay? N choose 1 is actually equals to n. If you have n players on a football team and you need to choose 1 to be a goalkeeper, there are n possible choices, okay? N choose n is equal to 1. If you happen to have 11 players on a football team, you need to choose all 11 players to play, right? There's only one way, and that is to choose everybody out there. Okay, these are some special results that you need to be aware of. But more importantly, and this is related to binomial theorem, is this. N choose r is the same as n choose n minus r. Okay, so for example, 10 choose 2 is the same as 10 choose 8. Okay, 50 choose 30 is the same as 50 choose 20. Why is this so? If you have a team of 10 players, you need to choose 2 people to be your captain and vice captain, right? It's the same as choosing 8 players to be the non-captain and vice captain. That's all. Okay. If you have a class of 50 students, you need to choose 30 students to be prize receivers, right? It's the same as choosing 20 students to be non-prize receivers. That's all. Get it? Can? So there's always this mental switch. Choosing the number of players to be given the tickets, right, is the same as choosing people to be rejected. That's all. Okay? Can on this? So which means that n choose 0, right, is the same as n choose n actually, hence giving you 1. N choose 1 is the same as n choose n minus 1. Okay? To choose one player to be the captain is the same as choosing n minus 1 players to not be your captain. And the only guy left out must be your captain then. Okay, can? All right. So this reflective component of n choose r, right, is very important in understanding the binomial theorem now. All right. Okay. So the binomial theorem, right, is very flexible in a certain sense, and that's why you don't have to remember the formula once you understand the dynamics behind it. So the binomial theorem is like this. So it's written as such: a plus b to the power of n. So firstly, this guy will expand to become like this: n choose 0, a to the power of 0, b to the power of n, plus n choose 1, a to the power of 1, b to the power of n minus 1, plus n choose 2, a to the power of 2, b to the power of n minus 2, plus n choose 3, a to the power of 3, b to the power of n minus 3, plus dot dot dot, plus n choose n minus 1, a to the power of n minus 1, b to the power of 1, plus n choose n, a to the power of n, b to the power of 0. Okay, so this is, I'm not exactly sure whether this is the way the O-level formula sheet presents it, but at least this is the one way to remember it quickly, okay? So at a quick glance, there are a couple of observations you can do right, and you can fill up right away, okay? So one thing is there are actually a total of n plus 1 terms, okay? If you look at it, the index element here, right, ranges from 0, 1, 2, all the way to n, okay? So it's a total of n plus 1 terms. Post-extension, okay? This is the first observation that you can make. Okay? The second observation that you can make is for each individual term, right, the powers of A and B would always be equals to n, which is the power of the original bracket. Okay, so look at my yellow highlighter, you will see it. All right. So powers of A, B always sum to n. Okay, can so far? And the last thing that you can observe, right, is the power of A always follow the index element. What do I mean by index element, right? The number below the n in each n choose R, okay? So it's this. Okay, so pardon my convoluted highlighting. If you look at this, okay, so the power of A will always follow that's what we call that's what I call the index element. Okay, index element is not a common term that's being used, but it's the number that keeps jumping with every term. Okay, can follow so far? So power of A follows index element. Okay. Okay, guys, any question on this task bar?
No.
Okay. Okay, but this is usually not how at least for the first two terms, is not how the formula sheet tends to present, okay? Because A to the power of 0 is just 1, and n choose 0 is just 1 also. So the formula does not write in such a form, in a complete form as I do. It tends to be simplified and be written as such. So this whole thing, it will just become b to the power of n plus n choose 1 a b to the power n minus 1 plus n choose 2 a square b n minus 2 all the way to the last term is n choose n. N choose n is 1. B to the power 0 is also 1. And a to the power n, so it's a to the power n then. Okay? So if you contrast what I have in blue versus what I have in red, right? I personally feel that the one in blue conveys more information right now. It helps you to grasp the pattern of the binomial expansion. Okay? As compared to the one in red in a simplified version here. When you look at this, it feels that certain message is lost and you cannot grasp the pattern. Okay, so because you are learning this for the first few sessions, it's good to write everything out in full blown like this. Okay, even excuse me, even though it's very trivial, you think that a to the power 0 is just 1, right? Just go ahead and write it down first. Even a is a to the power 1, feel free to write down a to the power 1 so that you can see for yourself how the numbers and the powers gel together. Okay, it's very important for binomial theorem. Okay, Ken? So Yanni says your teacher covered to this level already.
Yes.
Oh, okay. Pavan, yourself, do you still recall all this from binomial theorem?
Yeah.
Oh, okay. And Yanni says your teacher talk about the symmetry of the binomial theorem yet?
No.
Okay. Okay, so okay on this, both of you? Yanni, do you need to copy anything? Don't worry, I'll send it to you later on. Okay. Ken? Okay, so in this case, right, you can see for my, okay, so I'll give you a numerical example. So if I have x plus 3 to the power of 4 then, okay? So total I should have 5 terms. In my case, in my previous example, I tend to let the n choose r follow the power of a, right? So that's how I will do it now. So this will be 4 choose 0. Why isn't the thing appearing? 4 choose 0, x to the power of 0, 3 to the power of 4, plus 4 choose 1, x to the power of 1, 3 to the power of 3, plus 4 choose 2, x to the power of 2, 3 square, plus 4 choose 3, x to the power of 3, 3 to the power of 1, plus 4 choose 4, x to the, sorry, 4 choose 4, x to the power of 4, 3 to the power of 0. Okay, so you can see once you know how the trick to the expansion, right, is very natural. The trick is always the index element here must jump from 0 all the way to 4. And the powers of x will follow it, and the powers of 3 is complementary to it, as in that the power must sum to 4, that's all. Okay, and then you can simplify this. So
Mr. Lu.
Yep.
This one is the same as the one that we went through last Wednesday, right?
Yes, but I'm just giving you a refresher right now. Still.
Then how come like the last Wednesday one, like the 3 is to the power of 0, like for the first
in my index element, I follow b instead of a, right? Like in this case, my n choose r, the r follows a instead of b, right? That's what you're saying, is it? This is the whole point of today's lesson, Nuni. So don't worry. You just follow my formula above first will do.
Oh, okay.
This one first, okay? So so the 0, right? My index element, the n choose r's r, follow the first term, the a that pop out first.
Okay.
So I'm just following it here. Can see?
Yeah.
Okay, so if I were to simplify this, right, this will just give me 3 to the power of 4 is 681. 81 plus 27 times 4, 108x plus 4 choose 2 times 9, 54x squared plus 4 times 3, 12x cubed plus x to the power of 4, okay? This is if I had choose to let the index element 0 follow the power of x, okay? Which is the way my formula sheet above indicated, okay? That means I let my index element follow the power of a. So because this is like a plus b to the power of 4, okay? Can? Okay, all agree on this. So I don't think there are number carelessness in my simplification. Now, so the key to mastering binomial theorem, right, is the fact that the binomial theorem is actually symmetric. I can actually opt to let my index element, right, the n choose r, right, follow either the power of a or b in every single term actually. So in this case, in my expansion here, I opt to let it follow the power of a. Okay, so you can see that my x follows the n choose r all the way. But in fact, it could be the other way around actually. So x plus 3 to the power of 4 still, right? I can actually let to opt the n choose r follow the power of b, which is actually 4 choose 0, x to the power of 4, 3 to the power of 0, plus 4 choose 1, x to the power of 3, 3 to the power of 1 now. Then plus 4 choose 2, x to the power of 2, 3 to the power of 2, plus 4 choose 3, x to the power of 1, 3 to the power of 3, plus 4 choose 4, x to the power of 0, 3 to the power of 4. So Yanis, this version now will just be like what I went through with you last week, right?
Mm-hmm.
And you will see that if you expand this out, it's exactly the same as the one in blue just now, actually. So if I expand this out, I will have x to the power of 4 plus 12x cubed plus 54x squared plus 108x plus 81. Okay?
Okay.
So you can see that in this expansion here, right? This guy here is always following the second guy instead. Okay? If you know the power of either x or 3, you will always know the power of the other guy because they must sum to 4. Okay? And it is this symmetry of the binomial theorem that a lot of students just lose it already. Okay,
Isn't the only difference because in questions won't they tell you like expand it in terms of ascending powers of x and descending powers of x?
Okay, so this one we KIV first. So you will know how to actually execute the situation based on the instructions of the question if they want to force you in a particular direction. Okay? But otherwise, we will keep to this. Like you are free to roam both directions right now, unless the question dictates otherwise. Okay. Okay. So you can see that the second way of expansion, right, is just the opposite side of the blue direction actually. And why is this so, right? It's because of the fact that n choose r is the same as n choose n minus r. Why? For example, 4 choose 1 here must be the same as 4 choose 3 down here. Okay, 4 choose 2 is the same as 4 choose 2. 4 choose 3 is the same as 4 choose 1. So the coefficients are symmetric, you see. Okay, so it doesn't matter. As long as you stick to one way and you proceed the expansion, you'll be okay. So it doesn't matter which way you choose, unless the question point you in a particular direction. But of course, you cannot say, I know that there are 5 terms, right? Then the first 3 terms, I let my n choose r follow x. Then my last 2 terms, I go and follow 3. Cannot. If you pick in a particular direction already, you must proceed in a particular direction throughout. You cannot switch direction midway through the expansion, of course. Get it? Okay. So I cannot remember whether the O-level formula booklet gives you the blue version or the red version, but I think it's probably the red version. Okay. So I actually prefer the blue version because A comes first, right, in the writing of the expansion. So letting A follow the index element fits my style a little bit more. You know what I'm saying? Okay, Ken? Both of you understand this idea? Okay, so you must be very symmetric and systematic in your thinking. So with this in mind, right, given any binomial expansion, you can actually expand it very quickly already, and you can choose to let the index element follow whatever thing that you want to follow. So let's say if I have something like this, 3 plus 2x to the power of 7. So at one glance, automatically I will say, okay, I'll let the index element follow 3. So I will know that the first term must be 7 choose 0, 3 to the power of 0. If 3 has got power 0, this guy must got power 7. Why? Because these two numbers must sum to 7. Okay? Then the next number must be 7 choose 1, 3 to the power of 1, 2x to the power of 6. Because these two numbers must sum to 7. Okay? And I have already opted for that this guy's power must follow this guy. Okay? So you will plus, let's say you plus dot any random point. Okay, if this is 7 choose 5 right now, if the term is 7 choose 5, 3 must be power what?
5.
5, and 2x must be power?
2.
2, and that's it. Okay, then plus dot. Get it? Okay? So how is this going to help you to solve some questions right away, right? For example, if I have 3 plus 2x to the power of, we'll use this one anymore. Okay, 3 plus 4x then, to the power of, let's say, 100. Okay? Then you are not going to, if I say expand this out, you will go nuts, right? Because there will be a total of 101 terms waiting for you. And that's clearly not efficient. And that's not the way we study math for, okay? So if I say I want the x to the power of, let's say, 68 term, okay? Can we construct this immediately then, okay? That means we look at the sensing of the binomial theorem, right? And then we ask ourselves, who will be the one contributing to x to the power of 68, okay? So you know that every singleton term in the 101 terms ought to follow a pattern that's like this. It should be 100, then choose something here, right? Then you will have 3 to the power or something, 4x to the power or something, right? Okay, so in this case, the question wants for power 68. So Pavan, what do you think the rectangles, the third square should be? This yellow box here.
68.
68, okay, because only this guy contributes to x. So only he will determine the powers of x in every subsequent term. And since the question asks for 68, this guy must be 68 then. Okay, and this is 68, then the power of 3 must be?
69.
This guy, 69?
Because isn't the 4x and minus 1? Oh, yeah. Okay, never mind, yeah.
Okay, what do you think it should, no, it's not 69, what do you think it should be?
Wait, will it also be 68?
Okay, why so?
Wait.
Because if you look at it, what is the observation number 2 here? The powers of A and B must always sum to
And
n. So
also it's just 100 minus 68.
Okay, if the 4x takes up power 68, then 3 must take up power 32 automatically.
Okay.
Okay, so this guy must be 32 immediately. Get it now? And
yeah,
this guy here, you are free to write either 32 or 68 because the question did not ask you to expand this out at all.
Okay.
Okay, you can write 32 or 68 and both are accepted. You have not dictated which direction you are expanding. Okay. Get it now? This is the way to do binomial questions then. You're not supposed to expand this out. Okay, you're supposed to be able to pinpoint how to construct the term required backwards. Okay, guys, Yanis, okay with this? Has the teacher went through this already?
Yes, briefly.
Oh, okay. So understand. So you must be able to construct the terms quickly, and this is where your laws of indices will come in. Okay. But to answer, so let me just sidetrack for a little while and answer something that Pavan listed out just now. So suppose the question was 3 plus 4x to the power of 7. Okay. Then we say list the first 3 terms, okay, in ascending powers of x. Then part B is in descending powers of x. Okay, so this is how the question is actually in a way determining how you should expand. So if I were to do part A, right, you know that the first term ought to be, so it's just, in total, since this is power 7, if I really go and expand it out, I will have a total of 8 terms. But that's not what the question wants. The question wants only 3 terms. So the first term, if you look at the pattern, right, it should be like, oh, 7 choose something, 3 to the power of something, 4x to the power of something, right? Then plus 7 choose something again, 3 to the power of something, 4x to the power of something, then plus something. Okay, so this guy, this guy, and this guy, this guy, this guy, and this guy. Okay, Yanis, if you look at part A, right, the solution, so if the question wants ascending powers of x, should you give maximum power to 4x or 3 first?
4x.
Like this guy here, what do you think this power should be? If this is your expansion and this is your first term.
Oh, 3 should be the low what that ascend the smallest.
So the smallest will be
3.
no, as in what do you think what power should be in the yellow box?
0.
So 4x to the power of 0, like this.
Uh-huh.
Okay, then 3 will be the power of
7.
7. Okay, then this one up to you to choose between 7 or 0. So let's just say I choose 0 then. Okay, then the next term, how would the 4x to the power of
1.
1? If this is 1, then the other guy must be power
6.
6. Okay, then this guy now must be 1. Now you cannot write 7 choose 6. Okay,
Okay.
because if you look at my first term, it's clear that I've already opted that the power of 4x must follow the index element. So it must be coherent throughout. Don't switch halfway.
Okay.
Okay? And then the other guy must be 2 here, 5 here, and 2 here then. Okay, this is how it goes. Because the question asks for ascending powers of x. So you must start from the lowest possible point and move upwards in that sense.
Okay.
Get it now? Everyone okay with this?
Yeah.
Okay, so if it's part B, if they want descending orders of x, then you know that, okay, so 7 choose 0, I must give 4x the maximum power, which is 7, and thus 3 must be relegated to have power 0. Then 7 choose 1, 3 to the power of 1, 4x to the power of 6 plus 7 choose 2, 3 to the power of 2, 4x to the power of 5. Okay, something like this. All right. And don't forget dot, of course, because the question asks for the first 3 terms, but we must account for it, the remaining terms. Okay on this? All right. Okay, so this is one kind of binomial question you can expect for yourself. But the main skill today that I want you to pick up is at least to pick up how to pinpoint a particular power quickly. Okay, so there are 2 levels of complexity with regards to this kind of questions. The first is, let's say if you have 2 plus half x, getting boring already. Okay, so half x to the power of 10, and I want x power 7. Okay, Yanis, construct. What do you think x power 7 should look like? Then Pavan, you will do power 4. Okay.
We are supposed to like make x like power 7 in
Okay.
like the E brackets.
So,
Or
yeah.
huh?
Is that a question or is that?
Yeah, a question.
No. So for example, I don't know if you expand this out, you have a total of 11 terms, right, in a binomial expansion.
Yeah.
So what I mean is I don't want you to expand out. I just want you to tell me how would the x power 7 term look like? Its coefficient.
Oh, so it's like
So you know that every generic term in this binomial expansion should be like, 10 choose something, right?
yeah.
And you have 2 to the power of something, half x to the power of something, right?
Yeah, correct.
So what do you think the square should be occupying then?
The x, the half x square should be 7.
7, and the other guy must be?
3.
Okay, and then?
7.
Okay, so you choose 7, okay? Also can, okay? So the question will be like this, then you're supposed to evaluate this thing on a calculator, that's all.
Oh,
okay. So you have the coefficient, that's all, okay? Understand? That's what we mean now. So to construct the power 7 term, means you must do this right away. Okay? Understand now? Okay, Pavan?
It will be 10 choose 4.
Okay.
And then 2 to the power of 6.
Okay.
And then half x to the power of 4.
Yeah, that's it. Understand now, guys? Okay.
The 10 choose 4, right? You could either put 10 choose 4 or 10 choose 6, right? Both can.
Yeah. But if you look at what Yanis did, because he actually followed the 7 to the power of x, right? So Yanis already opt that this guy here should follow the powers of x. So you should try to follow his style then, okay? But otherwise, you have put 4 or 6, of course, okay?
Okay.
As a grader, it will be very weird if we see that, how come this guy keeps switching around throughout a question? It doesn't make sense, okay? If there is no reason to switch, then you should not switch.
Okay.
Okay, Yanis okay with this? Understand now? Okay, how this kind of question can be worded. So we will move on to a few more questions on this. okay, is definitely very easy when you have only one x term in a binomial extension and it's x power 1. Life will never be so nice, okay? So let's say if you have 2 plus x squared to the power of 8, then we say 1 power 6, 1 power 8. Okay. Okay, Pavan, you will do the first one. You need to do the second one.
So, so x choose 5.
Say again.
X choose, sorry, not x, 8 choose 5.
8 choose 5. Okay.
Yeah.
So 8 choose 5 and then
And then 2 to the power of 5.
2 to the power of 5. Okay. And then
x squared to the power of 3.
x squared to the power of 3. Okay. So why is it 5 and 3? Because these two numbers must definitely sum to 8. Okay. And then he's actually following this index element to follow the power of 2. Get it? And then lastly, he has already done a lots of indices inside his head. This guy here is actually give you x to the power of 6, okay? Not x to the power of 5. So this is where your lots of indices, if you didn't learn it well, it's going to come and haunt you again and again and again here, okay? So I cannot emphasize this enough. X to the power of a, b is x to the power of ab, okay? Not a plus b, which is the most common mistake in this case, all right? And Yanis, your turn.
So is it it can be the 8 can be a bigger number, right? The 8 choose something.
Okay, what do you mean though?
Like let's say like it be like 8 choose like 14.
It cannot be. The n choose r, right? The r must always be smaller than the n. It
Oh,
could be that you have only 8 soccer players, you're going to choose 14 goalkeepers, right?
Okay.
But the point is the x square is already there to help you already. So let's say it's definitely 8 choose something, right? Then 2 to the power of something, right?
Mm-hmm.
Okay, something, and then x square to the power or something else, right?
Yeah.
If I want x to the power of 14, so what do you think this something else should be then?
Mm. 7.
7, understand?
Uh-huh.
Once you figure that this is 7, everything checks out already. Right? That means 2 must be to the power of
Oh, okay. 2 1.
1, understand? Then 8 must be to the power of
1.
it can be 1 or can be 1 in this case, following his style. Now understand now? Okay? Get it? Okay, so maybe when you don't have a single simple x, it's always this harder this way, okay? So we'll go through a few more numerical examples on this together. So let's say if you have 3 plus 1 over 2x, okay, to the power of 7. I want x to the power of negative 5, x to the power of negative 3. Okay, Yanis, you will do this one, all right?
So
I sidetrack for a while. Do you all know your CCA commitments in the June holidays already?
Wait, what?
Do you all know your CCA commitments during the June holidays? Like, you all need to like show up for CCA.
Oh, I don't have CCA is like cancelled in my school.
Yanis, yourself?
It's online.
No, but what day would it be or when? Do you know it?
No.
Okay. Because I'm trying to arrange everything such that like my 2 Sec 3 classes can be combined together because I teach you all trigonometry. Then I can reserve the slot, the free up slot, right, to revise earlier topics if you need to actually.
Okay.
It's more efficient this way. Okay, so Yanis, x to the power of negative 5.
X to the power of negative 5 is 1 to the power of x to the power of 5. So it's
Okay, so 7 choose something, 3 something, and 1 over 2x to the power of something, right? What should this be?
This one should be -5.
Would it ever be -5?
No.
But the x is already in the denominator already, right?
Uh-huh.
So this is just 5 right away. Right?
Then the negative is...
The x is in the bottom already, right? So the x will give you the negative right away. Right? So you see, this guy, right, is actually 3 plus half x to the power of -1 to the power of 7, isn't it?
Mm-hmm.
Then if you see, I have 7 choose something, 3 to the power of something, half x -1 to the power of something, right?
Mm.
If I want power -5, what must this be?
Oh, 5.
That's it, understand? Because the laws of indices will help you in this case.
Oh, okay.
So if this is 5, the other guy must be
2.
2, and this must be, let's say, 2 or 5, up to you then. Understand now?
Oh, okay.
So the takeaway from this example is this: whenever you have a x in the denominator powers, right, I want you all to maintain the habit of rewriting it into a form like this. Okay, it's more visible and assuring to the brain actually. If you think of it like this, it's very hard to visualize the situation. Okay. Okay, Pavin, yourself.
So 7 to the power of 4. I mean 7 like choose 4. And then 3 to the power of 4. And then 1 over 2x minus 1 to the power of 3.
Yeah, that's it. Okay. Yanis can follow? Okay. So when I do questions like this, right, let's say I practically always work backwards in mind. So let's say if you want me 2 plus x to the power of 100, you tell me you want x to the power of 67. So I'm actually reverse engineering. I know that there's 100 choose something, 2 to the power of something, x. So this one is 67 right away. Get it? Then this must be 33. Okay, then this will be 33 then. So in terms of my brain thinking, this comes first, this comes second, this comes last actually. Okay, understand? But in terms of the structure, you must be able to fill all this in first actually. Get it? Then these numbers here are just a black box that you need to fill in answering, in constructing the terms. Understand? Okay, both of you okay with this? Somehow if you're not following right away, or you're just not getting it. Okay? Okay? You must remember that this method, all right, only works because of the observations that we have from expanding the binomial theorem. Okay? Because we know that every singleton term in the binomial expansion, right, will always fulfill all these properties. Namely, these two numbers will sum to 100. Okay, and the number here will always either follow the powers of 2 or the powers of x in this expansion. Understand? Okay, and hence I can actually randomly plug any item based on the power that I want right away, and that's the whole idea behind this. Okay, any questions on this? Yes, no? Okay, so the examples that I've given thus far, right, is when x is only focused on one of the terms. It will not always be the case like this. Sometimes there is a twinkling involved where there are x present in both terms. So for example, like this, x plus 3x plus x squared to the power of 10. Okay, so I want so say I want x to the power of 13 then. Okay, so Yanis, you try. How should you split up between these two terms such that you can get power 13 at the end of the day?
So you put 10 choose something first in the first bracket. And then the second bracket is like 3x. The bracket is x squared.
Okay, so there's one yellow box here, one yellow box here, and one yellow box here. Okay. Okay, I just want to check first. Has our teacher went through something like this yet?
Oh, is it like this question type?
Yeah.
No.
So he has only been going through when there's only one x.
Yeah.
Okay, this is not, okay, that one will be very basic. So the more advanced one is when you have x on both terms, okay?
Okay.
There's a balancing act involved, how to split 10 such that net you can achieve a power 16. Get it? Okay, so I want you to train your brain to think how to do these things, okay? So Yanis, you try this one?
So we have to use like the both x's, right?
Yes, yes. And that's where the difficulty comes in, all right?
Oh, okay.
So feel free to do some try and error to get to, or whatever twinkle your brain works, okay?
Wait, the on top the 2 yellow boxes equals to 13, right?
Say that again.
Like the 2 boxes above is that equals to 13, right?
You mean this one and this one, is it?
Yeah.
With 10 what? Because power 10 one.
Oh, 10. Oh, okay.
Okay.
I cannot find any number.
Okay. Try again. Okay. So when you do not know where to start, right? The best is to split the 10 half first. So if you split the 10 half, it's obviously 5, right? So when you see 5, wait, yeah, I made a mistake. Oh, no. So when you see 5, right? What is the net power based on this 5 combination?
Um 10
Yeah, 10
10
and
and
5, right?
uh-huh
So x to the power 10 times x to the power 5 gives you x to the power of
15.
15 is too high, right? Compared to this one. Get it?
Yeah.
Okay. So this kind of things don't need to worry about the coefficients, only worry about the powers right now. So 15 is too high. It's not what you want, right?
Yeah.
You get what I'm saying? Okay, so if 15 is too high, it's not what you want, then do you think you should bump down on the x square or bump down on the x? So the next one must be 6, 4, right? Or 4, 6. So do you need to give the 6 to the x or the x squared?
X.
X 6, right? So this one is 6, this one is 4. Then what power do you have right now?
X to the power of 8 and 6.
Which is?
14.
Which is still too high, right?
Yeah.
Then bump down again, understand?
Oh, so 7 and 3.
And that's what you want already, understand?
Oh,
And
okay.
still can either be 3 or 7, doesn't matter in this case. Understand now?
Okay.
Okay, this is when you are desperate, then you just start by slicing half. Then you just ask yourself, where should you move for, of course. Sometimes there's a smarter way to do this, but sometimes there's not. There is actually a more presentable way to do this, but I just want you to get used to this kind of sensing right now. Understand?
Okay.
Okay. Okay. So Pavan, you try the second one. So I should have written this down just now. Wait, so okay. If I want x to the power of 18,
Can you use like comparing coefficients to solve this?
say that again.
Like comparing coefficients to solve this.
No, combined coefficient doesn't work in this case because I have not given you what the actual power looks like, right?
But if you do like, for example, 10 choose r times 3x to the power of 10 minus r.
Oh, okay. So what you mean is not comparing coefficient, but the general term, is it?
Yeah, general term.
That's something that I want to teach next week, but not this week. So this I just want you to train how to split the power, that's all actually.
Okay.
You will realize that the general term method, right, is more inefficient actually. It's very time consuming to write those things out. And you may have issues with the simplification process, you see. So I want to train the students to know how to split the power. It's a practice for your loss of indices also at the same time.
Okay.
Okay. So try it out.
3x. So you need 18. Or 16. Okay. 10 choose 2.
10 choose 3, okay.
10 choose 2, sorry.
10 choose 3, right?
2.
I can't hear you.
2.
2, okay. And then?
Yeah. And then 3x to the power of 2.
Okay.
And then x to the power of 8.
X squared to the power of 8.
Yeah, x squared to the power of 8.
So net this will give you power 18. Understand now? This can follow is the idea.
Yeah.
Okay, so I want you to train to think of these things, all right? There is another way, of course, but I will not go through today's lesson. Okay? Can? Okay, so one more. Okay, so now it's like 1 over x plus 3x squared to the power of 10. Okay, so 1 over x, right? Don't deal with this kind of things mentally. Rewrite it for yourself first. This is like x to the power of -1 plus 3x squared to the power of 10 then, okay? So let's say if I want okay, so if I want x to the power of 11, okay? So Yanis, you will try this one, So minus 8. Okay, Pavan, you will try this one, x power 4. Okay, in fact, both of you should try both questions. It's the last question of the day already.
Can I do it on the paper first?
Yeah, of course.
Is x to the power of 4 possible?
Is it not possible? Wait a minute. Oh, sorry, I meant -4.
Oh, okay. I was
Sorry.
wondering why.
Mr. Lu, is it the 3 and 7?
3 and 7 is correct. Okay. So you have 3 here, 7 there. This, let's just use 3 then. Okay. Unless there's a special reason for this, right? I tend to let this guy follow this guy, okay? Because it's more convenient, nearer to me, that's all.
Oh, okay.
So I think the school or the formula sheet, I need to check, tends to follow the other way around, but this is just my personal preference, okay? Side by side, right? So it looks nicer on the terms, okay? Okay, next, you try the second one. Must try also. Try the second x minus 4, okay?
Oh. Wait, should I do it?
Yeah.
Oh, okay. I'm ready. I got the answer.
Okay, just give Yanis a while first.
Okay.
Understand? So, Pavin, does this help you to clarify any doubts that you have?
Yeah, I think because at the earlier part of it, I was a bit unsure.
Okay. So what you were referring to on a general term, right? I will do that next week actually.
Okay. And then also, because my teacher was saying it's like trinomial when they give two different, like when they give a trinomial.
Yep.
Is that also, do you have to learn that one?
That will be on a very special situation. So don't worry too much about it first. Make sure you strengthen your fundamentals on this first.
Okay.
At the end of the day, it's just a binomial theorem. The chapter is called binomial theorem, right? So
yeah.
Don't worry so much about trinomial first. You focus on your binomial. Make sure you are well sorted on that sense first.
Okay.
One at a time on these things. Especially in the current situation. My God. Ready, Enis?
No.
Okay, because you know that it's power -4, right? Net. So of the cake of 10, right? Should you give more to -1 or give more to x squared?
X squared.
If you give x squared, would you overpower the -1? You get what I'm saying?
Oh, so you should give more to
The other way around. You should give more power to the -1 so that it will outweigh the x squared, understand?
Okay. Oh, is it 8 to the power 8 and 2?
8 and 2 is correct. Pavin, you got the same answer?
Yeah.
Okay, so 8 here, 2 here. So in my style, you'll be 11, choose 8 here. Okay, so this is the main goal for today's lesson actually. As long as you understand that the binomial expansion is symmetrical, okay? Doesn't matter which way you choose the index element to follow, that's one. And the second thing is, given any random expression like all these examples that we have here, you must be able to pinpoint and construct the power as prescribed by the question. Okay, and in our cases here today, we have been doing a lot of mental try and error. Of course, mental try and error doesn't mean that you go and try out every possible case. There are smarter ways to go about it as you gain more experience. Get it? Okay, so Yanis, you're learning this for the first time, you will get better and better on this. Okay?
Okay.